This is another math video, but not of the usual type, at least not my usual. Under normal circumstances, the kind of videos that I post, in math anyway, are pure educational videos. They represent me taking published research, usually that's been published for a long time, years, usually decades, and then presenting it to you in an educational format. I'm showing you how to do a calculation, I'm teaching you some bit of mathematical physics. And this is certainly very valuable, but it's actually not the only thing I do. I do screw around with stuff on my own. I mess with math problems that haven't been solved yet. I mess with them not because I seriously expect to be able to solve them, but just because I think it's fun and my mind kind of won't let up. It keeps going at them, even though the odds of actually solving them are slim. It's just something that I enjoy doing. Now, most of the time I never get very far. Most of the time I never really get anything interesting at all. It just blatantly fails. And sometimes one of my efforts actually yields something strange. Not necessarily a right answer. In fact, many times I can't even tell whether it's right or not. I can't tell whether it's close or not. But it still yields something interesting, something unexpected and kind of fun. And I would really like to share that with you here. I think it would be a really fun sort of community building type video where I post what I'm actually messing with and you tell me what you think of it. Maybe you know more about a particular topic than I do. So I think I'm going to occasionally start releasing videos where I do show you exactly just that. There's one problem, and this problem is the reason why I haven't released any of these types of videos yet. I'm worried about credibility. I want my YouTube channel to do well, and if I'm posting mathematical physics videos, that's only going to happen if people trust that my mathematical physics videos describe math accurately. So I've really just stuck to math videos where I'm presenting already known things. Things that, as I said, have been published for decades, and I'm just providing educational content. That way, anytime you click on one of my videos, you know that it's verified and relatively well known within the mathematical physics community. However, other channels in less advanced topics like chemistry or something often post videos of them doing reactions where they don't necessarily know what happened, or they just tried something that may not be a published reaction, or perhaps they thought they got the reaction they were trying to do right, but when they posted it, somebody noticed that actually something else happened and maybe it just looked similar. Either way, without issue, they can post videos of them just trying stuff for fun. It doesn't necessarily have to go exactly right, and part of the fun and part of the community building nature of it is that the audience can then look at what they did and say what they think. I don't see why this shouldn't also be done in mathematical and theoretical physics as well. To me, it seems like something that really should be on YouTube, and communities should be built around that. However, that does still leave the credibility issue. A lot of you people may be coming to learn and may not know enough about the topics to know when I'm talking about something that's already verified and is trustable versus something that's just my own fiddling. So to solve this problem, what I'm going to do is anytime I'm publishing something that isn't just a verified educational video, I will tell you in the introduction. I'll make it extremely clear that this is just my own fiddling and not verified content. That way, anytime you click on a video and it just explains math, you know that you can trust it. I hope this allows me to achieve the credibility that I need while also allowing me to post fun videos on the math I'm actually playing with in my free time, to hear what you have to say about it and also to entertain you if you like that kind of stuff. So now for a little bit about the contents of this specific video. The unsolved problem that I've been fiddling with is simply the Schrodinger equation for the helium atom, and more generally any multi-electron atom. But I've focused mostly on the helium atom problem. This problem has gone unsolved despite the fact that there's an exact closed-form solution to the hydrogen atom because of that electron-electron repulsion term. It's a three-body problem, and there's no way to get rid of or exactly solve out that repulsion term. And it's my fiddling with that problem that I'm going to talk about in this video. For a long time I fiddled with it and, surprise, surprise, didn't get anywhere, and I very well may not have actually gotten anywhere with the fiddling that I'm going to show you in this video, but the difference between this and my initial attempts to find some sort of useful way to break apart the equation is that I found a bizarre ansatz, a really weird one, that actually does, as far as I can tell, break it apart in an interesting way. A way that, again, as far as I can tell, seems to actually yield an exact solution. Does it really? Have I actually done the math right? I don't really know. I can't be sure. I've certainly looked at it carefully and I haven't found anything, but that doesn't mean there isn't anything. This is part of the fun. I want you to tell me what you think after evaluating my math. The ansatz consists of a first term, which has two hydrogen atom factors that are purely dependent on the separate nuclear distance vectors, and then a factor that's purely dependent on the electron separation vector, so the nuclear distance difference vector. And then there's another term that is actually a convolution integral, and it is designed to, when the Schrodinger helium operator is applied to it, the complete thing, so the Hamiltonian minus the energy, it turns into some terms that the negative of show up as a result of the same operator acting on the first term. And those terms need to be cancelled with this extra convolution integral term because otherwise they'd interfere with the way the ansatz is supposed to break apart the equation. I hope you find this bizarre ansatz that does weird things to the Schrodinger equation for the helium atom interesting. It's very modular, and it seems like it can be generalized to any multi-electron atom equation, so that means either it solves all multi-electron atoms, at least the modularly generalized version of it does, or it fails to in exactly the same way modularly as the helium ansatz does. Who really knows? It's your job to evaluate my math and tell me which one. So, let's get to it. Here follows the math section. So here we go with botching the living shit out of quantum helium. Here's the table of contents. I'll start with an introduction, and then I'll move on to a detailed work-through of the Schrodinger helium case, at which point I will insert the helium ansatz and simplify, and then solve out an equation that results from that for this quantity here, which you'll know what that is once we go through this a little bit more. It's a factor that shows up in the ansatz. In the process, we'll also find the complete energy eigenvalues. Then I'll show you how to generalize the ansatz and the solution to a generalized multi-electron atom. And finally, I'll talk about generalizing it to the Dirac equation. The Schrodinger equation for the hydrogen atom represents one of the glorious few cases where a fundamental equation of nature can actually be solved out exactly for a physically realistic system. It is truly satisfying, especially when you've dealt with differential equations for a long time in physics and you realize how rarely that actually happens. This solution will actually be used as part of the bizarre analysis of the helium atom Schrodinger equation presented here in this document/video. As a result, I will take this opportunity to quote the hydrogen atom Schrodinger equation and its solution. This is the Schrodinger equation for the hydrogen atom, and this is its exact solution with these energy eigenvalues and some other definitions that show you what the symbols that show up in here are. This solution represents the exact solution of a two-body problem, which is technically a multiple-body problem. However, it doesn't yield any general many-body problem insight. It is only exactly solvable because the heavy nuclear mass can be taken to be fixed, its motion at best accounted for via a reduced mass, thus turning the two-body problem into an analytically solvable one-body problem. The only many-body problem insight that this provides is that if you can turn your many-body problem into a one-body problem, you can solve it. This is obviously useless for higher many-body problems, where there will be irremovable interactions between mutually moving bodies in any frame you pick. In this document, I insert an ansatz, one that is a modified version of a previous failed attempt, into the Schrodinger equation for the helium atom that actually appears to yield a bizarre but effective breakdown of the equation. A closed-form exact solution does appear to be yielded. Of course, this is tentative. I could have made another mistake. First, the Schrodinger equation for the helium atom is this. The ansatz that I analyze here, assuming we don't bother to symmetrize or anti-symmetrize the wave function, which can always be done later, is as follows. It's this. I have this part added on there, which is defined as this, and I realize this is a bizarre ansatz. It actually makes sense, and I'm going to explain why shortly. The argument of this phi factor is often dropped for brevity, and this quantity here is the Green's function for the helium atom Schrodinger equation, meaning it satisfies this. So this is actually a sort of strange convolution integral, and in this, as you may have already noticed, I have denoted the Hamiltonian for the helium atom with this HE of R1 and R2 symbol there, so by this I just mean that. And for brevity, I will also often drop this argument. At this point, I really recommend against trying to plug this ansatz into the Schrodinger equation yourself just yet. Instead, I recommend continuing on with this video document until its end and then trying it. I want you to do this because it'll actually be a lot easier and clearer if you see me do it first. The only way I can think of to approach explaining my motivation for this bizarre ansatz is to first explain a closely related ansatz that I guessed first, but doesn't allow solution of the problem. The idea was to separate dependence on the two nuclear distance vectors and their difference vector from each other. So I tried this ansatz. Now, I also assumed that the dependence exclusively on each individual nuclear distance vector came in the form of hydrogen atom solutions, or one electron atom solutions. The atomic number is taken to be 2. And I also am not attempting a normal kind of separation of variables here because I have this other thing that exclusively depends on the difference vector. So it's introducing more non-trivial dependence on the nuclear distance vectors than just separate dependence on them. Now, one can see that this is exceedingly similar to the ansatz given above in the box, one that seems to have worked. The only difference is that this initial ansatz does not include this pi term. This initial ansatz actually fails to achieve separation because the Laplacian product rule has a cross term that interferes with the separation, a fact pointed out to me by Dr. Benjamin Bayman at the University of Minnesota. I really should have seen this. Base rate neglect, probably. I was actually expecting the math to get very complicated and non-trivial later on in the problem, and the first steps to be super easy in sticking this ansatz in. So I really just blew through those first steps so fast that even though I knew the math, and I knew that about the Laplacian, I wasn't even thinking. I just completely screwed up because I was going too fast through what I thought was going to be the easy part, and that's where I made a mistake. But anyway, this pi term I came up with later cancels that out. When the complete Schrodinger helium operator acts on this pi term, it turns the Green's function in the convolution integral into a delta function by definition, allowing the integral to be done easily. With the integral done, the pi term is reduced to exactly the offending cross terms but with the opposite sign. So we have this relationship here. They then cancel the offending terms out, allowing for a clean further separation and exact closed form determination of the energy eigenvalues and this phi factor here, assuming I haven't made further mistakes, which of course is very possible. For the sake of foreshadowing, I will give these values here. This is the phi factors, and yes, of course, it looks very similar to the hydrogen atom solution, and it is. It turns out the equation for phi that we get when we fully work through this looks much like the hydrogen atom. It's not exactly the same, but it's similar. As a result, the solution is not exactly the same, but is similar. The energy eigenvalues work out to be this. As far as I can tell, these energy eigenvalues match experiment about as well as one would expect the Schrodinger equation to do. Inserting this and the hydrogen atom wave functions back into the ansatz gives the complete wave function, assuming I haven't screwed up. As I said, this solution represents the complete and exact closed form result for both the energy eigenvalues and the eigenfunctions. However, to get the eigenfunctions, one has to compute the Schrodinger helium Green's function and these pi term convolution integrals. I doubt they can be done analytically, but they are all but trivial for modern computerized numerical methods. The energy eigenvalues are exact without requiring any such hullabaloo. Beyond this, the ansatz that I am presenting here for Schrodinger helium can apparently be generalized for the case of an arbitrary multi-electron atom. The highly modular nature of the Schrodinger Hamiltonian for multi-electron atoms and of the ansatz I am discussing here allows for this easy generalization. The generalized ansatz breaks up the arbitrary multi-electron Schrodinger equation in exactly the same way as for the helium case. I also think the helium ansatz and its arbitrary multi-electron atom generalization can be generalized further to the Dirac equation. I give the solution that I think results. However, I've not investigated that in detail. I will at some point in the future. So now let's do the detailed work through for the Schrodinger helium case. And this is where it gets really fun because you get to see the coolness of the ansatz actually happen right in front of your eyes. You get to see the problems cancel each other and this nice equation for phi fall out that's actually solvable. Now it is a messy business, but the results are so cool and the process itself is so cool, it's really worth just pushing through it. So this is the Schrodinger equation for the helium atom. Plugging in the ansatz directly just gives us this, and then I distributed that through to prepare for inserting this. And remember, this is the whole helium atom Schrodinger equation operator being applied to that. That'll transform that Green's function into a delta function and make the convolution integral not a convolution integral anymore, but just a really easy delta function integral to do. which gave us this relation, that key relation, so let's just plug that straight in. Now we can apply the product rule for the Laplacian and then simplify. This is where things start to get really messy. First, I rearranged it to make the application of the product rule convenient. Then finally, I applied the product rule, which got from here down to there. Now this looks messy, but this is right before that awesome simplification is about to happen. These are the terms from that pi term that are going to cancel the nasty ones that ruin the separation from those Laplacian product rules. This is the term from the Laplacian product rules, and you see they're exactly the same but with opposite signs. I set up the form of the pi term to do precisely that. So they cancel, and that gives us this much simpler result here. Now for another really cool simplification, but that is a bit less surprising perhaps. With these problem terms that ruined my original attempt canceled, we can move on to the next simplification step. This step takes advantage of the fact that the hydrogen atom factors in the ansatz solve the Schrodinger equation for the hydrogen atom. This is where the real cleverness of picking those factors to be specifically hydrogen atom wave functions comes in. So we see that these satisfy these equations here. Those are the Schrodinger equations for the multi-electron atoms that are going to zero out that factor. But in order to identify those, we need to split up the energy. So I assumed that this energy was the sum of two hydrogen atom contributions, and then this leftover part I just called the electron mutual interaction energy. I just labeled it that. And strictly speaking, you could always do this because you could always subtract these values off of the energy and just call that subtracted version this e little e. So you can always pull it out like that. You can break up a constant any way you want. This is perfectly valid, and it helps the algebra because then you can rearrange that after you've inserted this broken up energy eigenvalue into this form, and you can recognize these two hydrogen atom Schrodinger equations there, and that these operators are being applied to their solutions, so these yellow highlighted factors vanish. And this is important because then it simplifies this equation straight down to this one. And this one can then be simplified to this one just by dividing out those extraneous factors. So now we have what we will find to be an exactly solvable equation for this phi quantity and this e quantity. Let's move on to doing that. This is that equation for the phi quantity that we were just dealing with. It turns out manipulating this into a solvable form requires some extra tricks, and all those tricks are on the derivative term, so I'll isolate those. And these tricks are easiest to perform in Cartesian coordinates, so we'll work in Cartesian coordinates. This is the derivative term in Cartesian coordinates. Remember now that the phi quantity exclusively is a function of the difference vector components, so these. So we're free to write this, but that means we can do something really cool with these second derivatives in the chain rule. We can take this to that. They're equal precisely because this is exclusively dependent on the difference coordinates. But that means a bunch of the terms are identical. We can then combine like terms to ultimately get to this. Then we can plug that in, and we've turned an equation that used to look like this and seem very unsolvable to one that really does just look like a copy of the hydrogen atom problem, but with an opposite sign on the potential here, and with an atomic number of 1/2, which is a little weird. But it's the same mathematical form, so it helps us with our solving. This is the thing written fully in Cartesian coordinates, where I've defined these difference coordinates with a bar. Then we can change variables on those different coordinates to spherical coordinates, which gets us down to this here. Now this really just looks like the hydrogen atom problem. This PDE is simply the Schrodinger equation for the hydrogen atom with opposite nuclear charge and energy 1/2 e, and z equal to 1/2. So its solution is obviously just this. Now, this is not normalizable, but as I said, we wouldn't expect this thing on its own to necessarily be normalizable, so that doesn't matter, just the whole thing has to be. And e is just this. So now remember the values of EH1 and EH2, we get the total energy to be this. The wave function can then be completely written out as follows. So we have the ansatz here with this fudge factor for the normalization that I didn't bother to calculate. And then we have this value for that extra pi term. It's the same as given above. The difference here is that we now have this value for phi in addition to this value for the hydrogen atom wave functions. So now we've got a complete description of the solution. Inspection of this complete solution shows the following. In order for this wave function to be non-zero in L2, n hat, L hat, and m hat have to take on particular values in terms of separate electron quantum numbers. Otherwise, the first term, or the integrand of the second term, diverges, or both are zero for known quantum states. This is how the boundary conditions fix the energy. Specifically, the aforementioned inspection of the above solution reveals that they must be the following, these particular values here. Therefore, the complete energy eigenvalues are this formula we got in the introduction, and we have finally solved out everything now, which is really quite nice. So now let's move on to generalizing this via its modular nature to the general multi-electron atom. This funky thing is the general multi-electron atom Schrodinger equation. The associated wave function and energy levels can be found using essentially the same ansatz, but in a modular manner extended to include all the additional terms coming from more electrons being there. The natural extension is actually this ansatz here, where pi is now this mind-numbingly complicated thing. Of course, this Green's function still behaves like any normal Green's function. It satisfies this equation. And then note what I mean by lambda there. It'll help you understand these formulas. This general phi value ends up being this, not really very surprising. These general n, l, and m values are this, and then these are the general difference coordinates. And the energy eigenvalues end up being this, which is beautiful and complicated all at the same time. Of course, all of these being due to the mutual repulsion of the electrons, and these all being due to the attraction of the electrons to the nucleus. Now let's move on to the idea of generalizing this to the Dirac equation. The Dirac equation for the arbitrary multi-electron atom is this gorgeous thing. I think the same ansatz can be generalized to the Dirac equation quite easily. The only difference is that the Dirac equation is first order, so there are no pesky cross terms in the product rule. Therefore, there is no need for a pi term at all. However, I have not worked through this in detail, so I guess maybe something crops up, but I do have some significant familiarity with the Dirac equation. I've solved it for the hydrogen atom myself. I have a video on that. I will link to that in the description. Also, I've solved the Schrodinger equation for the hydrogen atom. I'll link to that in the description as well, although that's not relevant here. And I've also worked with the Dirac equation extensively in quantum field theory, so I know it pretty well, and I suspect that nothing would actually crop up in this, and that this ansatz, the one that I'm about to present, actually would work. But before I present that, I need to show a new notation in order for the expression for my ansatz to really make sense. So in matrix math, it seems like there isn't, at least that I'm aware of, a common notation for component-wise multiplication of vectors. So I need a way of multiplying this vector and that one together to yield that weird quantity. And because I'm not aware of a standard way of writing that in matrix math, I've just decided to use these double bars here to denote that. And that actually is the exclusive type of multiplication that I use in this ansatz. So this is exactly the same kind of ansatz that I showed for the general multi-electron atom for the Schrodinger equation, but without a pi term. And if this ansatz really does work the way it's supposed to, then the energy eigenvalues should turn out to be this, and this phi quantities here should turn out to be this in terms of the hydrogen solution to the Dirac equation, with these definitions of various things showing up in those quantities. And the hydrogen atom solution is just this, where I have these definitions here. And this I've derived, it's standard, that's in the video that I'll link to in the description. And that's about it. So you have seen now my fiddling with the Schrodinger equation for the helium atom and the general multi-electron atom. I hope it was interesting. If you do have any insight about this, please put it in the comments section. I'm eager to know. But regardless, if you found the video entertaining or interesting or some combination of the two, please give it a thumbs up and don't forget to subscribe. Dietterich out.